All right, good afternoon, everyone. I'm going to wait here just another 30 seconds or so. There's still people joining, but what you see on the screen is one of my old exam threes, where on one of the problems I gave them three related rate problems, and I asked them to do one of them. So I think I told you that's kind of like the way I like to do these problems. That way, if there's one that you do one on the test, if I give you one problem and it's the one you just really can't figure out, that's kind of going to be bad. So at least here you get to choose, and then hopefully one of these will be something that you feel comfortable with. So I just wanted to share that with you to start. That's what you should expect on our next exam. What else?
So there will be notes, okay, if we're doing more than one, but what if we do two and one is right and the other is wrong? Would you count the right one? Or?
Well, I put here no extra credit for doing more than one. So you have to pick the one you're going to do. If you do two of them, then you have to tell me which is the one you want me to grade.
Oh, okay.
Yeah. So there's kind of you got to make a choice. Okay, so today we're going to get into chapter 3. We're going to be talking about, we're going to breeze through 3.1 and 3.2, where we're going to review some of the things that we should know from college algebra about exponential and logarithmic functions. And then we're going to talk about the derivatives of exponential and logarithmic functions. So let's get into this. So chapter 3, we're going to start out with 3.1. So we're going to quickly go through this. That's what I say here in the notes, because this is a review. If you feel at all that you don't remember any of this, then you're going to need to go back and take some time to review. All right. So let's start off with what an exponential function is. So again, from college algebra, an exponential function is any function f of x equals a to the x. So you could have 2 to the x, 5 to the x, 10 to the x. You could even have fractions like 1/2 to the x. And this is what a generic exponential function looks like. It goes on the right-hand side, it goes up forever. On the left-hand side, there's a horizontal asymptote that goes out the left side like that. Does that look familiar to you? College algebra, this is f of x equals a to the x. And in the example that I'm showing you right now, where it kind of goes up to the right, here a is bigger than 1. So I'll give you a specific example. F of x equals 2 raised to the x. That is an example of an exponential function. Here, we would say that the base of this exponential function, the base is 2. So this is what we call exponential growth, because if you read this like a book from left to right, it grows, right? And notice that we can talk about some limits. What does the function do as we let x go to infinity? So as you move to the right, where is the function headed? Well, it's headed up, right? Up to infinity. That's what that first one is saying. The limit as x goes to infinity of f of x is infinity. Make sense? Now look at the other one. The limit as x goes to negative infinity, that means if we start moving out to the left, the function heads to 0. And you can see that because it's asymptotic. It's approaching the x-axis, getting closer and closer. So all exponential functions where a is bigger than 1 should look something like this. Let me show you in Desmos. Got this ready to go. Right now, here's an example of an exponential function. You can kind of see right now, this is what a is. I'm adjusting it right now. This is 1.84. If I continue to make a change, it still has the same shape, but the bigger a gets, the steeper it gets, the faster it grows. If I bring that a to a smaller number, it kind of flattens out. Let me do this. So the bigger a gets, the steeper it gets. The closer a gets to 1, the more shallow it gets. And then what if the number in front, the a, is a fraction? like 1/2, this is what happens. You get this graph in blue. So that is, hold on. Okay, there we go. So the one here, this blue one here is a function f of x equals a to the x, where here a is between 1 and 0. So if you use a number that's a fraction or a decimal like 0.25 or something like that, then you're not going to have exponential growth. You're going to have what we call exponential decay. So that means as you go to the left, this thing goes to infinity, which is that, is that one right there. And then as you go to the right, this thing flattens out towards 0. That's what this limit's saying. Is that clear? Do I need to expand on that at all? You need to know what exponential functions look like if the base is bigger than 1 and the base is between 1 and 0. We're good? Okay. Now, there are properties of exponents that you need to remember that are useful when we're dealing with exponential functions. A lot of these you've already seen, right? If you have, something raised, two things being multiplied together, they have the same base and you have different powers, you add the powers together. If you divide two things that have the same base, a and a, then you subtract the powers. So examples of this, x squared times x cubed is x to the 5th. This one, x cubed over x is x to the 2nd, because you just take the 3 and subtract the 1. So trying to show you properties, these properties in action here. This one says if you have something to a power, so if I have like 2 to the 3rd to the 2nd, you multiply those two powers. This is 2 to the 6th. And then this last one says if you have like 2 times 3 to the 4th, you can do 2 to the 4th times 3 to the 4th. So those are just properties of exponents. Again, college algebra stuff. That all should look somewhat familiar to you. Just make sure you remember those, all right? Okay, next thing. Let me see. There is a special function that you learn in college algebra. Let me go to my notes here. There is a special function, special exponential. I know when I put it up here, you're going to recognize it. It's called the natural exponential function. The natural exponential function. And it is the function f of x equals e to the x. You should have learned that in college algebra, learned about this function e to the x. And you should have been told in college algebra that e, like the number pi, is just it's just a decimal. It's about 2.718, and it keeps going forever and ever. Just like pi does, it goes forever. It doesn't have a pattern to it. It's a very special number in math. Now in college algebra, you're not told why it's special. You're just told that it is special. And I'm going to tell you today why it's special, but just not yet. Hang tight, all right? This function right here, if we were to graph it, would it be exponential growth or decay? Would the graph be growing as we move from left to right, or decaying?
Growing.
Growing, right? Because this number right here is bigger than 1, right? So we definitely should get growth. The graph of that exponential function, I'll just graph it right here, y equals e to the x, is that one, that particular one. Of course, if I change the value of a, it's going to change the shape. But if we let a be 2.718, we get the very special exponential function, all right? Okay, I'm moving on. We need to talk about logarithmic functions. So the idea of the logarithmic function comes from this. If you start out with some domain, like in other words, some numbers that you're going to plug into a function, right? Some function f, then what comes out over here, we call this the range of the function. And some functions have what are called inverses, which take you back. And we notate an inverse with a little negative sign. So I'll give you a specific example of a function and its inverse. If you take the function f of x equals 2x, then what that does is it takes things in and it doubles them, right? So it takes 2, it sends it over to 4, takes 3, sends it over to 6, takes 10, sends it over to 20, right? That's what the function f does. The inverse of this function should send all those numbers back to where they came from. And the inverse function in this case, can someone tell me what it is? The function that would basically undo what we just did?
1/2 x.
Half of x, right? It's half of x. So the original function doubles the value, right? Takes 2 to 4. So to take 4 back to 2, we need to take half of it, right? Take 3 to 6, take it back. 6 to 3, you take half of it. So functions can have inverses. They don't always, not every function has an inverse. This is one example of one that does. Let me give you an example of a function that does not have an inverse. If I take the function f of x equals x squared, then what happens here is the function f would take, let's say, 2 over to 4. It would take 3 over to 9. It would take 4 over to 16. The inverse function, right? The inverse function, if there is one, should take these back. So what would you think would work?
Squared. Oh, sorry, square root.
The square root, right? The square root. But here's the problem. If I try the square root of x, I agree, 4 will go back to 2, 9 will go back to 3, 16 will go back to 4. But look, we also could have plugged in -2, right? Where would -2 have gone? To 4 as well, right? So you have that 2 goes to 4 and -2 goes to 4. So if the inverse function should take 4 back to where it came from, but it came from 2 places. So you can't go back to 2 places. To be a function, you can only go back to 1 place, or you can only be sent to 1 value. So this won't work. And the reason it doesn't work visually is if you were to graph x squared, back in college algebra, you learned this thing called the vertical line test. This is the test you run to see whether or not you have a function. So if I draw a vertical line, I never hit more than once, right? And so it would pass the vertical line test, which means it is a function. But then there's another test called the horizontal line test, where you draw horizontal lines. And if you ever hit more than once, then this would mean you have no inverse, because I hit more than once when I draw horizontal lines. So there's an easy way to look at a function and tell whether or not it has an inverse. If it passes both tests, the vertical and horizontal, then it definitely has an inverse. Does this all ring a bell a little bit? Somewhat sound familiar from the past? Okay, so let me do one more thing. What if we take, instead of taking that parabola, f of x equals x squared, and instead of drawing the whole thing, instead of doing that, why don't I only draw half of it? In other words, let me only draw this function for x bigger than or equal to 0. Then the graph would just be the right side of the parabola. Now, if you look at this right side only, does it pass both the vertical and horizontal line test? Yes.
Yes.
So it should have an inverse. And the inverse, in fact, would be the square root of x. But see, now you don't have a problem. You don't have a problem with this whole thing with -2 and 2 going to the same number 4. You don't have that problem because you've restricted the domain. You're not allowed to plug in -2. So now 4 can only go back to 1 place. And so there is an inverse here. The inverse is the square root of x. And if I graph this, if I graph that, this is what it would look like. That's what they look like together. So I'm going to go to Desmos and have it graph graph these because there's something important about this. Let me see here. I want a new graph. I want a new graph. If I graph x squared, whoa, x squared, and only let x be greater than 0 or equal to 0, I get this. If I graph the square root of x, I get this function. And there's something very special about the way these look. If you were to draw a diagonal line, y equals x, if you draw this diagonal line, see that diagonal? We call that diagonal the identity function, y equals x. It's just a perfect 45-degree line. Notice that the original red function that was x squared restricted, right? Restricted only to the right of 0. And notice that the blue function, that they are mirror images of one another over the dotted line. So if you like turn your head to the side, they look like a reflection of the blue and red are reflections of themselves. Do y'all see that? That happens for every function. If it has an inverse, if you graph the two, they have to look like that. Okay? Questions?
Will they always like intersect?
They don't have to always intersect. They do not always have to intersect. I'll give you another example. If I take 2x, okay, there's 2x. Remember, that was the first example I gave you. There's 2x. Its inverse is 1/2 x, right? Oh, oops, 1/2 x. So, I mean, these are intersecting at the origin, but that's, if you look over here, they don't, right? They don't always have to, but they are still reflections, right? And I could give you examples where they don't ever intersect, but well, actually, the one that we're about to do, you'll see. Okay, any other questions? So basic idea is everyone here needs to know what a to the x looks like, right? A to the x. If a is bigger than 1, we've got growth. A is between 0 and 1, we've got decay. We need to know the limits. In other words, what happens as you go to the right and to the left of a to the x. We need to know that when you're talking about a function, it may or may not have an inverse. If it passes both the vertical and horizontal line test, it does. And if we graph the inverse, it should be a reflection of the original function over the identity. Yeah, that's that all. Everything in a nutshell so far. And then there's some properties of exponents we need to know. Let's go back to that graph of e to the x. And, or not e to the x, a to the x, there it was, right? And I can change the value of a, right? I'm either going to have growth like that, or I'm going to have decay, depending on how I draw it, right? I'm either going to have decay, or I'm going to have growth, decay, growth, yes. But no matter how I do it, do you agree that in either scenario, this is a function passes the vertical line test and has an inverse, yes? So let me show you the inverse of this function. Let me show it to you. That's what the inverse of this function looks like. I'm going to go to there's the more natural view. That's what the inverse looks like. And you can kind of see, yeah, it's a reflection, right? It's a reflection. So the question becomes, if this is the function f of x equals a to the x, then what is its inverse function, right? What is it? Well, that's what a logarithmic function is. A logarithmic function is an inverse function for an exponential function. It is the function that undoes an exponential function. So we have a very special notation for it, right? It's not as simple as, like, remember when we had x squared, the inverse of that was square root of x. When we had 2x, the inverse of that was 1/2 x. This is all very algebraic, right? X squared, square root of x. 2x, 1/2 x. This is algebraic. I'm saying if you have a to the x, geez, come on. If you have a to the x, the inverse is something, and it has to do with logarithms, all right? In fact, what it would be log base a of x. That's the inverse function of a to the x. So let's talk about logs. All right, let's talk about logs. Let's get into the notes for this. Log. Oh, whoa, what did I just do? Okay. All right, so what does a logarithmic function look like? F of x equals log base, that a right there is what we call the base of the log base a of x. Now what you're looking at here is the graph of a logarithmic function where the a is bigger than 1. That's what it looks like. So if the base down here is bigger than 1, this is what you get. And if I go back to the Desmos, you can see right now, this is what we get when a is bigger than 1. We get exponential growth on the exponential function. So here's what the inverse function looks like, the reflection. Where is it? So notice a few things here. There is a domain restriction on this one. Go back to this picture. Notice the blue picture does not exist to the left of 0, right? We have in this picture we have a horizontal asymptote here. This thing is taking off, getting closer to the y-axis, but never actually gets there. And as we go to the right, this thing goes up and gets bigger and bigger and bigger and bigger. So look at what I have here when I have these limits on this. The limit as x goes to infinity, that means as we move to the right, this graph just keeps growing and growing and growing. It's not very fast. Logarithmic functions don't grow very fast, but they do in fact grow as you move from left to right, as long as the a is bigger than 1. That's what you have. And then the other thing is this one here, the limit as x approaches 0 from the right. See, we can't go to negative infinity. The graph does not exist over here for logarithms. You can only approach 0 from the right-hand side, and look at where our graph goes. It takes off and goes to negative infinity. That's what that second limit is. Okay, so as long as the base of the log is bigger than 1, this is the picture. Go to the right, it grows forever. Head towards 0, it drops down. Okay. Now, what happens if I change that a and I make that a fraction, like half or 0.2 or something like that? Let's see what that looks like. There. That's the graph that we get if the a is between 0 and 1. So now it changes. As we go to infinity, go out to the right, this thing keeps going down forever, heads towards negative infinity. Slowly, but it goes that way. As I head to 0 from the right, now it takes off to positive infinity. All right. Questions? Basic.
Will the domain and range always be like infinity, but never negative infinity? Well, the domain. So the domain will never be negative infinity.
Okay, so I'm going to answer that. Very good question. Let me answer that question on a different page. So when we're talking about exponentials, okay, exponential functions, that's f of x equals a to the x. We know it's going to look like one of two things. It's either going to be growth, right, if a is bigger than 1, or it's going to be decay if a is between 0 and 1. Okay. In both cases, the domain is everything. You can plug any number you want into an exponential function. It will have no problems. And you can tell because the graph goes to the left and to the right forever. Agree, everyone? Yeah. Now, the range is the outputs. And the range of an exponential function is everything from 0 to infinity, meaning that the only y values that come out of these are above the x-axis. Your graph is always above the x-axis. You never touch the x-axis, so it's never 0. And it's never below the x-axis, so it's never negative. Got it? Now, when you look at a logarithmic function, which is an inverse of an exponential, you have two possibilities here as well. If A is bigger than 1, and then here if A is between 1 and 0. If A is bigger than 1, your graph looks like this. If A is less than 1 and bigger than, oops, I did that wrong. If A is between 0 and 1, this is what it looks like. The domain of an inverse function, I'm sorry, of a logarithmic function is everything from 0 to infinity, because the graph only exists to the right of 0 on both of these. And your range will be everything, negative infinity to infinity, because you always get all possible y values come out, because the graph goes in both directions forever. And so notice these are opposite, right? The domain of an exponential function is everything, but in a logarithmic function, it's the range that's everything. Here, the range is 0 to infinity, but that's the domain of the other one, of the inverse. Which I hope makes sense, because visually what's happening is this. If you have a to the x going this way and a log function going back, then if this is everything, negative infinity to infinity, and all that comes out is 0 to infinity, then the domain of a to the x is actually equal to the range of the log. It's the input of a to the x is the output of the log. So the domain of this is the range of that. Do you see what I'm saying? Like, that's why there's a correspondence there.
Yeah, it makes a lot more sense now.
Okay. Was there another question? Ash, were you going to ask something?
No, that was similar to my question.
Okay.
Thank you.
So we need to know what these logarithmic functions and exponential functions look like. Just if we see one, we need to know what it looks like. We need to, oh, as x goes to infinity, it goes up forever. Oh, it goes down forever. Oh, as we approach 0, it goes up or down. We need to know that without having to sit there and like type it in somewhere and graph it. All right. Now, there is a special log function. It's called the natural log function. And here's what it is. F of x equals, I know you've seen this, ln x. That's not an I, that's not in, it's ln. It stands for logarithm natural. Like, you know how in French, a lot of times they do it backwards than we do it. Instead of saying natural log, they say logarithm natural. So that's why it's ln. All this is a log function. Does anyone know what the base of the natural log is? All log functions have to have a base, okay? They all have to have a base. You have to have a number here to define a log function. So do you know what the base of the natural log is? I'm sorry? I just heard like a, that's all I heard.
I'm saying, is it E?
Yeah, it's E, okay? The natural log is actually the log function that has a base E, okay? Look, log functions can be any base. 4, you can have log base 10, you could have log base 7, you could have log base a half, okay? Just like exponential functions would look like this, 4 to the x, 10 to the x, 7 to the x, 1/2 to the x. So what I'm giving you here is like, this is the log function, this is the exponential function. These two are inverses of each other. These two are inverses of each other. These two are inverses of each other. These two are inverses of each other, right? That's the idea. So we always put a number down here, with the exception of 2 logs. There are 2 logs we don't put the number there for. The natural log, we instead of writing this, okay, instead of writing that, we write this. Does anyone know the other one we use a special one for that we don't write the number? This one here, log base 10. We don't write log base 10, we just write log x. So it's understood that if you write log x, you mean log base 10. And if you write ln x, you mean log base e. Now that, I wish we never did that, okay? I wish we never, ever adopted that convention, because students lose track of what the base is. They forget what the base of the natural log really is. The natural log is just the inverse. It's the inverse of e to the x, right? E to the x is that very special natural exponential function, and its inverse function is the natural log function. So why did we stop writing it this way? Like, why did we decide, you know what, let's not do this, and then for this one, let's not do this, and let's do this instead? There's a reason why. I'll share it with you. It's a historical reason. Back before, well, when we started using typewriters, okay, people who were doing research and would be doing like physics or chemistry or biology, the natural log would come up a lot. Log base e, log base e, log base e would come up, and they might have to write log base e hundreds of times within a paper. Well, if you've ever used a typewriter, do y'all know what it takes to subscript in a typewriter? If you wanted to actually write, like type on your typewriter, y'all know what a typewriter is, right? Log base e of x. If you wanted to do that, you would have to type on your typewriter, log, you'd have to stop, you'd have to turn the drum of the typewriter a half turn, hit the E key, turn it back, and then X, and then keep going. And then if you had to do it again, you'd have to do it, stop, do that, you know. And if you had to do that like hundreds of times, that would be a pain in the ass, wouldn't it? So what we did is we said, look, forget that. Since we're using the natural log so much, and we're using log base e so much, and we're using log base 10 so much, we're just going to do ln x for this one and log x for this one. And then when you're typing, you never have to stop, right? Ln x, just keep going. Log x, keep going. That's kind of, I don't know, I mean, I wish we wouldn't have done it, but I can understand why. It's stuck, unfortunately. Okay. So we're going to just go back to this. I want to graph again. I want to graph again the very special function e to the x, there it was, and then its inverse function, which is the natural log x. Those are like the most important functions for us in this class. Y equals x. There's the identity. I'll make it dotted. That's just to help convince you that those are inverse functions. They're reflections of one another over the identity function. Okay. That's e to the x, that's natural log x. Does anyone know why the base 10 log is so important? I haven't even explained why the natural log is important, or e to the x. But does anyone know why base 10 log is so important to us?
Acids and bases.
Yeah, acids and bases, we use log base 10, but why log base 10? Why not use log base 4, log base 7? Why base 10? It has to do with our number system. Our number system is base 10. Have y'all heard that before? Our number system is base 10. I'm going off on a tangent. I'm sorry, I have to. Okay, this is actually pretty mind-blowing if you think about this, all right? What does base 10 number system mean? We've been using it our whole lives, but we maybe didn't even understand that we were using it. If I write the number 3,471, we all understand what that means, right? That's 3,471. One way I could look at this is this. I have 1, 1, right? I have what, 7 10s. I have 4 100s, and I have 3 1000s. Do you remember like seeing that in grade school? Like the first position is how many ones you have. The second position is how many 10s you have, right? You don't remember seeing this at some point? Well, look, I'm going to highlight something. These numbers all have something in common. What does the number 1, 10, 100, and 1,000 all have in common? They're all powers of 10, aren't they? Those are all powers of 10. So when you could rewrite this as 3 times 10 cubed plus 4 times 10 squared plus 7 times 10 to the first power plus 1 times 10 to what power?
0.
0. Okay. So look, what I'm trying to get you to see is when we write a number down, right? Let's say I write a number down. Let's say a 4-digit number. This is how many 10 to the zeros I have. This is how many 10 to the ones I have. This is how many 10 squareds I have. And this is how many 10 cubes I have. So when I fill this in, 3, 4, 7, 1, we all understand that that means you have 3 10 cubes, 4 10 squareds, 7 tens, and 7 tens and 1 1 1. That's base 10 number system. I won't talk about decimals, but if you go the other direction, it actually works. If you put a decimal point here and start going this way, this is how, you take a guess, this is how many 10 to what's I have. Follow the pattern, 3, 2, 1, 0.
-1.
10 to the -1. Isn't that the same as 1/10? You've heard that. This is how many tenths you have, right? This would be 10 to the -2. This is how many 1/100ths you have. How many thousandths you have, right? This is the base 10 number system. That's base 10. That's not the only base though. We could do base 2. Let me say one more thing before I go on. In the base 10 number system, if I write a number out, okay? Right? If I fill in a number like 3, 4, 7, 1, what are the only numbers that I'm allowed to use in these slots? What numbers can I use?
Whole numbers.
Okay, which ones though? Like what are the only possibilities I could use to plug in right here?
0 to 9.
0, right? That's not a 0, but I'm counting them. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? I can only plug in 0 through 9. That's 10 things, right? There's 10 things I can plug in here. There's 10 things I can plug in here, 10 things I can plug in here, 10 things I can plug in here. The reason there are 10 things is because in base 10 system, we only work with the digits, these digits. All numbers can be made of these digits, right? Those are them, right? Every number in our base 10 number system uses those digits. So what is a base 2 number system? Well, how many things are possible? If in base 10, there are these 10 digits we can use. In a base 2 number system, how many things are possible? How many things can you use? Only 2. What are they?
0 and 1.
0 and 1, right? 0 and 1. You're only allowed to use zeros and ones. Computer science majors, binary, this is what computers do, right? So in base 2, if I write a number out, I can fill in these digits, but I'm only allowed to use zeros and ones. So I'm just going to make something up. 1, 0, 1, 1. What the hell does that mean? Well, we're in base 2, right? Think about this. When we were in base 10, the first position was how many 10 to the zeros we had. The second position was how many 10 squareds we had. Third position, 10 to the first, 10 squared, 10 cubed. The 10 was the base, right? So in binary or in base 2, this is how many what to the zeros we have. How many what to the ones? How many what to the 2s? How many what to the 3s?
2s.
2. This is 2 to the zeros, 2 to the first, 2 squared, 2 cubed. See, the base matches here. So what is this number right here? That is, I have 1, 2 to the 0. And then I'm going to add to that no 2 to the first. I'm going to add to that 1, 2 to the second, and add to that 1, 2 cubed. What's 2 cubed?
8.
8, 1 times 8 is 8. 2 squared, 4. I have one of those. 2 to the 1 is 2, but I'm multiplying times 0, so that's 0. 2 to the 0 power is 1. 1 times 1 is 1. Add those up, what do you get?
13.
13. This number here in base 2 or binary is equal to this number in base 10. So the number 1101 is the number 13. That's the way a computer works. A computer does not know the number 13. The computer knows 1101. And why do computers like binary? Why do computers use binary? Why do they only use two things, 0 and 1? Why do they use that? Why not 0, 1 through 9?
Because it's an on and off value.
That's right, because a computer only understands two things. You either have something there, like an electrical signal that's there, or you do not. It's yes or no. It's a light switch, on or off. All this fancy shit we do on our computers, Zoom, all these video feeds, right? All this audio going back and forth all over the city, all over the, you know, wherever y'all are, right? It's just a bunch of zeros and ones being sent at practically the speed of light, and the computer is just figuring out what it all means, right? But the language is base 2, because a computer only knows on and off. Why do we use base 10? We could use base 2. You could be raised from a child. You could be raised to just know base 2. And then you would see 1101 and you would just kind of understand it completely different, because you would be thinking like a computer. Why do we use base 10? We could have used any base. Could have used base 8. There's actually base like 16, hexadecimal. Why do we use base 10? Anyone know?
It's practical, easy to read, maybe.
But if you were raised to do base 2, you'd be telling me the same thing. You'd be saying base 2 because it's easy to read.
We got 10 fingers.
That's it. It's because we have 10 fingers. That's it. Okay. The average human has 10 fingers, right? If we didn't have thumbs, well, if we didn't have thumbs, we'd be in a worse situation. But okay, let's say we only had 8 fingers. I promise you, we would use it base 8. That's what we would know. That's what we would understand is base 8. If we had 12 fingers, we would have a base 12 number system. That's the way we would have, from birth to now, that's what we would understand. There's nothing special or significant about base 10 other than the fact that that's how many fingers we have. So that's the way we naturally started counting. And so we assign to each 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's nothing that even says those symbols had to be used. We could have used any symbols for 0. You could have used, there, I don't know, I need to make up a symbol. Like you could have used any symbol you wanted for any of these, right? Like we just chose those symbols. Okay, I'm going way too far off. My point was that in our thought of logs and exponential functions, the bases can be anything. When the base is e, things are very special. When the base is 10, things are special. 10, because that's our number system is base 10. E, I still haven't explained why E is so important, right? Why is that E so important? And I'm still not ready to. I'm almost there. I still got to talk more about logs. Back in college algebra, there are some other properties of logs that you need to know. I'm going to copy these because I want you to see these. These are so important. There was a point in college algebra where you did something called expanding and condensing logarithmic expressions, where you would take a log that had two things being multiplied inside, and you'd rip it apart into 2 logs with addition between them. Or if you had a single logarithm and you had division inside, you could rip it apart into 2 logs and change it to subtraction. Does that look familiar? And then the last property, this one is the most important one for us, is that if you had any logarithm of x to a power, you can bring the power out in front. I'm going to show you these same 3 properties. I'm going to show you them for the natural log, because the natural log is the one that we use so much. If I say you have natural log of x, y, I could rewrite this as natural log of x plus natural log of y. That is a property of logarithms. Natural log of x divided by y is the same as natural log of x minus natural log of y. And then the final property here is natural log of x to the r power is r times the natural log of x. The power can come out front. That is used so much in this class from here on out, and in Cal 2, we use that a lot as well. These properties you need to know, you need to understand and feel comfortable with. We good? By the way, these properties go both directions. So you can start with 2 logs and push them into 1. Or you can have 1 log and rip it apart into 2. If you go from left to right, this is called expanding. And if you go from right to left, that's called condensing. You should have done that in college algebra, and you probably didn't like it when you did it.
Sir, does
Yes.
that apply for the properties of exponents as well with the expanding and condensing?
It does not. Okay, so like if with exponentials, if we did e to the x times y like that, this becomes, well, this just becomes e to the x times e to the y,
Mhm.
right? It doesn't become addition. See this? See how this pulls apart and what it does is splits and it becomes addition? This does not, okay, does not become natural log of x times natural log of y. That is wrong. But with exponentials, it does work that way. Do you see how this became this?
Yes.
Okay, same thing if you did this. This becomes e to the x over e to the y. Now, those are the properties we just talked about earlier. That's these properties right here. Does that answer your question? Are you okay with that?
Yes, sir. Thank you.
Okay. All right, so this is where I talk about the, the natural log. Okay, so there's one more formula that I want you to know, and it's this change of base formula. Like I said, you can do a log with any base, all right? But when you look at your calculator usually only has the key natural log on it. So this is a formula that allows you to change any log. Whoa, hold on, sorry, I've lost what I'm doing here. Okay, this formula here says that you can change any log. You can figure out any log if you just have your natural log key on your calculator. So if I wanted to know like what is log base 4 of 10, all I'd have to do on my calculator is natural log of 10 over natural log 4. Because I have the natural log key on my calculator. So I just get my calculator out and figure out what that is. All right, I think I'm ready. Y'all ready? I've just laid down the framework of what exponentials and logs are, some of the properties, what they look like graphically. Now, what we're really here to investigate is what are the derivatives of these functions, right? Because calculus, we've been doing derivatives. So I have a little animation for you to kind of get us going here. Here we go. All right. What you see in front of you is the graph of the function f of x equals x squared. Okay. That's not an exponential function. You all agree that's a parabola? That's not exponential. I'm going to remind you that the derivative of this is just 2x, and we should all be very comfortable with that idea, right? So what we could say is this. If I go to some point on this graph, let's say I go and plug in the number 3, right? We know 3 squared is 9. You'll see that? 3 squared is 9. What's the derivative? What is the derivative of this function at 3? What's the derivative of this function x squared at 3?
9.
No, that's the value of the function at 3. If I plug 3 into this function, it spits out 9. The derivative is the slope of the tangent line here, right? So what would it be? At 3, what's the slope of the tangent line? Y'all are thinking too hard.
Positive. So let me count. So it's positive 1, so 3.
Y'all are still trying too hard.
So
Isn't-
It's 6.
It's 6. Okay, it's 6. Why is it 6? Because this right here is the derivative, right? So just tell me the x value. What, at 3 you want to know? The answer is 6, right? Yes. In other words, if I showed you that, you see the slope of this tangent line? This tangent line, the slope is 6. I'm sorry that's so small. If I zoom in, I don't know if that doesn't get bigger. Let me try this. Let me go control. Yeah, that's making it a little bigger. There we go. So if I'm looking at this function, then when I'm at 3, the value of the function is 9, but the slope of the tangent line is 6. What would the value of the function be at 4? What would the value of the function be at 4?
16.
16, okay. And the slope of the tangent line?
8.
8. Agreed? What would the value of this function be at 1? The
1.
value of the function. What is it?
1.
1. What's the slope of the tangent line there?
2.
2. Yes? Okay. You're probably like, what are you doing, man? You know, like, what the hell are you doing? Just watch. What I'm going to do now is I'm going to show you the graph of e to the x. There's e to the x. Okay, there it is. Now, what is the value of this function at 1?
E.
E, which is about 2.718. Okay. What is the value of the function at 2? Let's see. We are looking at the function f of x equals e to the x right now. The value of the function at 2 is what? 7.38. Yes, yes, yeah. Okay. Watch this. I'm going to show you its derivative now. Take a look at that. I'm going to move this point right now, and I want to see if you can see something pretty remarkably amazing happening. Who sees it? Anyone see it? What is it? What's really interestingly
The slope
weirdly-
and the
Value.
value of the function are the same.
the slope and the value of the function are the same. Look, this number, that means how high that point is off the ground. The height of that point is equal to the slope of the tangent line. That did not happen in the previous example, did it? When we had x squared, whatever value, I'm going to show you x squared again. I really want you to understand this. This is such a huge deal. If I go back to x squared, right? If I went to some point like 1, the value of the function there was 1, but the slope was 2. They didn't match. If I went to 3, the value of the function there was 9, but the slope was 6. They don't match, do they? If I go to 4, the value of the function is 16, but the slope was 8. What if I go to 2? At 2, the value of the function is 4 and the slope is 4. Hey, they match there, don't they? They match there, but that's the only place they match. If I continue to move this, look, 9.3, 6.1. 15.6, 7.9. There was only one place they matched, right? Everywhere else they were different. But if I draw e to the x, and I move this, notice the y value and the slope are always the same. Always. Always the same. So doesn't that mean that if I wanted to know, if I said, hey, everyone, go to 2, okay, let me take the derivative out of here. If I asked you right now, what is the derivative of this function at 2? What would you tell me?
7.38,
7.38.
whatever.
Exactly. All you're going to do is take 2 and plug it into the original function because, wait, what does that mean? What does that mean about the derivative? If this is the original function e to the x, then the derivative of it should then be what?
X times e.
No,
The natural log of x.
no. I want you to think about this. Look, when I plug in 2 into this function, it spits out 7.38. But you're telling me that's exactly the same value I'm going to get if I take the derivative. Yes? It's the same output. So if I go to the number, 2.65, and I want to know the value of the derivative there, all I need to do is just tell you 14.15. But where did 14.15 come from? It came from e being raised to 2.65.
So is it gonna be e to the x or
Exactly.
E to
It's itself. It is itself. The derivative of e to the x, if you want to know the slope of the tangent line on this curve, all you need to do is just plug that value into the original function. So, but I know this takes a little while to get your head wrapped around this. The question is, why is e to the x so important, right? E to the x is so important because it is the only function, the only one. There's only one. It is unique. You're never going to find another one out there. It is the only function where the slope of the tangent line, okay, the slope of this tangent line will always be equal to the y value of that coordinate of that point, whatever x value you're at. You go to the y value, that y value will always match the slope of the tangent line for every point on the curve. Doesn't matter where you are, they will always match. It is the only function that behaves that way, the only one in existence. Okay, so you might ask yourself, well, where did e to the x come from, right? It actually happened backwards. Mathematicians were asking the question, is there a function that behaves this way? We were like, I wonder if there's a function that when you take the slope of the tangent line, it's just equal to the height of that point. I wonder if it exists. I wonder if it exists. I wonder if it exists. And we actually went looking for it and we found it. And this is it. This is the function that does it. It's the only one. And it's unique. So we can't explain why it's the only one, just that it is. And that means you have to use that base 2.718, blah, blah, blah. If you use that base, you're going to get the function that behaves that way. We can't explain why it's that way. It somehow just naturally occurs, right? Can't explain it. So that's why we call it the natural exponential function, because it does exactly what we were looking for, a function that would be its own derivative. Now, it only works for e to the x. If you change it and you do f of x equals, let's say 2 to the x, the derivative of that is not just 2 to the x, unfortunately. So e to the x is the only one that is its own derivative. Hold on. How do I know? Okay. I'm kind of going in a different order than my notes. All right, so let's just kind of like recap what I've just said here, all right? What I've said to you is this. If f of x equals e to the x, then the derivative of that is e to the x. Another way you could write this is if you take e to the x and you take its derivative, you get itself. So you know right now, if I asked you what's the derivative of sine of x, everyone would be like cosine x, right? Just roll off your tongue. Now, if I ask you what's the derivative of e to the x, everyone's gonna be like e to the x, right? We now need to know that. But what is still unresolved then is this. If f of x is some arbitrary exponential function like a to the x, not that very special one, but just an arbitrary function, then what's the derivative? That I haven't established. But I'm going to tell you right now what it is. Okay. It is itself. I told you it wouldn't be itself, right? But it is itself, but there's one thing you have to do. You have to multiply that by the natural log of a. Let me give you a specific example. If I ask you for the derivative of 4 to the x, it will be 4 to the x itself, but not quite. You have to multiply times natural log of 4. And natural log of 4, everyone keep in mind, is just a number. If you get on your calculator, do natural log of 4, just be a number. So it's basically saying that the derivative of 4 to the x is itself, but we have to scale it. We have to either like stretch it out or shrink it. Another example, what's the derivative of 10 to the x? Itself times natural log of 10. What's the derivative of e to the x? Well, itself. Okay, that one is the same. Now, there is a reason, if you actually try to use this formula, it would work, because if I put natural log of e here, right, that would be what I would put here. The natural log of e is 1. Again, this is college algebra. If you go on your calculator and do natural log of e, you'll get 1, which is why this thing goes away and just becomes e to the x. You don't need to show that. You can just put e to the x. Okay, very important rule. And these are in your notes, in your formula sheets. Where is it? Here are the derivatives. Here they are. I just did this. Derivative of e to the x is itself. Derivative of a to the x is a to the x natural log a. Okay. Now let's talk about the logarithms. Right? We now know what the derivative of any exponential function is. Now let's talk about the derivative of logs. And I think, watch the way I'm going to do this. I'm going to actually prove this one to you. If y equals, let's say natural log of x, I want us to find y prime. I want us to find the derivative of the natural log of x. Right now, I'm not going to just give you the answer. I want to actually prove to you what it is. So what I'm going to do here is I'm going to do something kind of unnatural. I'm going to take e on both sides of this. So I'm going to do e to the y equals e to the natural log of x. So I get e to the y equals, now, when I put e and natural log together, what happens? These are inverse functions. What happens when you put two inverse functions together? Cancel each other out, right? And you just get x on this side. Y'all following what I'm doing? Now what I'm going to do is implicit differentiation. I'm going to find the derivative with respect to x. See if you can follow me on this. What is the derivative of e to the y with respect to x? What do you think? What's the derivative of e to the y?
E to the y?
E to the y, right? Itself, right? But chain rule, do not forget chain rule, everyone. Times, now what you do is you take derivative of y. What's the derivative of y with respect to x?
dy
dx.
dx.
dy dx. Okay, equals, now the other side, what's the derivative of x with respect to x?
1.
1. Okay, so we're trying to find y prime, so that means I'm trying to find this thing, trying to get that by itself. So I'm going to divide both sides by 1 over e to the y. You okay with that? We're almost there. dy dx equals 1 over, what did we say e to the y was?
X.
X. So this is just x. In other words, if you take the derivative of the natural log of x, you get 1 over x. That's in your formula sheets. Right? Well, they do the absolute value, but that's it right there. The derivative of the natural log of x is 1 over x. I know this can be a little overwhelming. Let me go back to this page here. I said, all right, look, derivative of e to the x is itself. Derivative of a to the x, well, it's itself, but then you have to multiply times natural log of a. Let me throw in here now the next thing we got. If f of x equals the natural log of x, then the derivative of it is 1 over x. What's the derivative of natural log of x?
1 over x.
1 over x. What's the derivative of natural log of x? 1 over
1
x.
over x.
Burn it in. Burn it in. Okay? Burn it in. What we don't know is what if we do just some arbitrary log, not that special one, but what if I take some other log that has some other base to it? What would the derivative be? Well, I'm not going to prove it to you, but I'm just going to tell you what it is. It's almost the same answer. I'm sorry, it's almost the same answer. It's 1 over x, just like this. But next to the x, you have to put natural log of a. Down on the bottom, put natural log of a down there. These are your 4 new major results from today. All right, these are the 4 major results that on your formula sheets, it's this whole section 9, 10, 11, 12, this right here. The derivative of e to the x is itself. The derivative of natural log of x is 1 over x. Those two are intimately connected to one another because that's the natural exponential. These two are connected. These are more general. This is for any exponential function. The derivative of a to the x is itself times the natural log of a. And the derivative of any log function is 1 over x natural log of a. So it's kind of like you have to throw that in there for the general logs and the general exponential. Are y'all doing all right? I know this is very different than what we've done like the last few days because it's a lot of information. Seems weird. I think we just need to practice some problems now. All right, so let's see if we can put this together. Find y prime. Okay, that's the instructions. Find y prime. Let's do a couple of problems. Here, y is equal to x, ln x. So the good news is this. We now know the derivative of exponential and logs. That's the good news. Hey, be quiet. The bad news, I know y'all can't hear that. Hey, chill out, dude. Hey, I'm talking. The bad news is that everything else we've learned is in play. Product rule, quotient rule, chain rule, everything is on the table now. We just have new functions. So if I want to know the derivative of this, I need to see the product rule. Do you all see the product rule there? That's x times natural log x. So when I take the derivative, and hopefully by now I don't have to go into too much detail with this, it's the derivative of the first one, which is
1.
1 times
The natural log of
the
x.
second one, natural log of x, plus, now the derivative of the second one, what's derivative of natural log of x?
1 over x.
1 over x. How do you know that?
I've memorized it.
Yeah, we just talked about that, right? It said derivative of natural log of x is 1 over x. Derivative of natural log of x is 1 over x, right? So we're doing derivative of this now is 1 over x, and then finish the product rule off times
X.
first one, right? X. Everyone see that product rule there? This is just 1 times natural log of x, natural log of x, plus, hey, wait a minute, 1 over x times x, isn't that just 1? It's just 1, isn't it? That's your derivative. Let's do another one. How about y is equal to, let's go x squared e to the x. What's the derivative of that? Who wants it? Someone volunteer. It's a product, right?
Um, 2x plus e to the x.
2x. Are you doing product rule? Careful.
Yes. Times,
Oh, okay. So 2x e to the x. Go ahead. Sorry. I thought you said plus
Oh,
e to the
yeah.
x. I apologize. So 2x times e to
Times.
the x.
plus e to the x times x squared.
Okay, perfect. So did the derivative of x squared first, 2x times e to the x. Plus now the derivative of e to the x. What's derivative of e to the x? Itself, right? Times the first function, x squared. That's it. Now on this one, do y'all agree I could do this? I mean, this wouldn't necessarily be something that you would think to do right off the bat, but I could pull an x e to the x out of both of those because both of these terms have an x and they both have an e to the x. So I could factor out and I would get that, wouldn't I? If I pull an x from here and the e to the x out of this term, I'm going to be left with a 2. And if I pull the e to the x out here in one of these x's, then I'll be left with an x. I'm just showing that you could factor that out. Don't need to. This would be fine, but questions? Who wants this one? Who wants that?
Would we start with e to the x? Well, e to the x squared plus x plus 1.
Okay,
The
so you're treating
derivative
it like a, what rule are you using then?
chain rule.
Chain rule. Okay, so what everyone's, and Robert's got this, what Robert's seeing is you got basically e raised to this big clump of stuff, right? E to something. And trying to take derivative of e to something, Robert's saying it's what? Would you say it is?
The same thing. So
The same
e
thing,
to the
it's
x squared plus x plus 1.
Okay. All right, so I agree. You have taken the derivative of the e part. Keep going.
And then multiplied by 2x plus 1.
2x plus 1. There's your chain rule. The derivative of e raised to something is itself times now the derivative of what was up here, which is 2x plus 1. Chain, right? So this was product up here. This was product here. This is chain happening here. How about this one? Ooh. X cubed e to the x cubed. Who wants this one? I want to hear from different people here. So what do you got?
So it's gonna be chain rule first.
Okay, where do you see a chain rule?
It's multiplying the x to the power of 3.
Yeah, this is multiplication, right?
Yeah.
So you have a product rule there. Yes?
Yeah.
Okay, just start running the product rule for me. Start running it. So
So 3 to the x squared
3x squared, that's the derivative first one,
times e to the x squared
Cubed.
3. Yeah, it's
Okay.
cubed, yeah.
everyone
then-
got that? That's the derivative of the first one times the second one. Okay, plus, now be real careful here,
It's gonna be e to the x cube.
okay, that's you, what you're doing now is you're saying, hey, what's the derivative of e raised to something, right?
Yeah.
And you're saying, oh, it's itself, right?
Then times 3x squared.
Exactly. Then you did chain rule times the derivative of what was up here, 3x squared. Are you done?
Yeah. No, 3x squared again. Or
Not 3x squared. The first function, right? Without a
oh,
derivative,
x cubed. Yeah.
x cubed.
There you go. Oh, I got a little bit confused there.
No, you did good. You
Yeah.
did good. Who has questions? I'm gonna clean it up, but who has questions while I'm cleaning this up? I just put the 3x squared times x cubed together, made it 3x to the 5th, and just slapped it out in front of the e to the x cubed. And I could even factor a 3x squared e to the x cubed out of everything, because they all have a 3, they all have at least an x squared, and they all have e to the x cubed. So if I pull it out of here, I'll be left with the 1. And if I pull the 3x squared out of here, e to the x cubed, I should be left with x cubed in there. Y'all doing all right? How about this? The natural log of sine of x. Who wants this one?
Would it be 1 over sine of x?
Okay, so you're looking at it like, okay, you've got natural log of some crap in here, right?
Yeah.
And you're saying, okay, the derivative of natural log of x is 1 over x. So the derivative of a natural log of crap is 1 over crap. Yes?
Yes. Yes.
Okay, and so you said that was 1 over what?
Sine x.
Sine x, okay.
And then from that you multiply by cosine x.
Multiply times, now you go inside and take derivative of sine, which would be your cosine x. But that's just cosine x over sine x, which back from pre-cal is cotangent x. Cosine over sine. Sine over cosine is tangent. Cosine over sine is cotangent. So let me try and give you some little generalization that might help you with this. I know this helps some students. If you ever see e raised to the u, let's say it's some, you don't know what it is up there, it's just something. The derivative of this will be itself, but then you always have to do chain rule and do derivative of what was up there. So if this is e to the junk, you take the derivative, you're going to get the e to the junk, but then you always have to multiply by the derivative of the junk that was up here. And for log, it would go this way. If you do natural log of u and you want to take the derivative, it's always going to be 1 over that u, whatever that u is in here, just put 1 over it. And then chain rule would say, now take it and multiply times derivative of what was inside. That might be helpful to you to have those written that way. I believe, let me go back to the formulas. No, the formula sheets don't do it that way. Okay. All right. Ready for some more? Y equals the square root of natural log of x. Find the derivative. I want people to take a swing at this. I'm trying to hear from everyone. I'm not calling on anyone, but I really want you to try and just take a swing. I don't want to always have the same people answering. Not that I don't mind, it's great, but you know, I want you to go for it, you know?
Is that one gonna be 1 over ln x?
Okay, so what do you see here? Do you see a product? Do you see a chain? What do you see?
I see a chain.
Okay, what's the outer function?
The outer function
The very last thing that would happen.
is the product rule.
I don't see a product. Right? If you plugged x in, you would do natural log of x on your calculator, and then you would take the square root, right?
Yes,
So there's not a multiplication in that. That's just a function inside of another function. So Nico, do you agree that the square root is the outer function
yes,
and the inner function would be the natural log?
yes.
So when you do chain rule, you always start with the outer function. So what is the derivative, Nico, of the square root of a green blob of stuff?
It's gonna be 1 over x.
1 over, well, let me ask you this. What's the derivative of square root of x?
It's 1 over x.
1 over 2
2
root
radical
x.
of x.
Right? That's the general formula for the derivative of the square root of x. Here we have the square root of this green stuff.
So it's gonna be 2
over
the radical of ln x.
Okay, good. You've done the outside one. Now take the derivative of the inside one and slap it next to this.
So it's gonna be 1 over x.
There you go. That's it. That's the derivative.
Nice.
Starting with the square root, you say, what's derivative of the square root of something? 1 over 2 times the square root of that something, whatever's in there. Then chain rule says, then you multiply times the derivative of what was inside. The derivative natural log of x is just 1 over x. Questions, anyone? With this one? It is not the same problem. Who wants that one?
So I see product rule and a chain rule. Am I correct?
Where do you see a product?
The ln and times square root over x.
Okay, I would agree with you, but what is ln just by itself? Like if I'd written this down, ln x times square root of x, or yeah, if I wrote that down, I would agree with you that there's a product right in here, because natural log of x, that is an expression that makes sense. But having ln just by itself is almost like me asking or me writing sine down without giving you anything inside of it, right? Just sine.
Okay. Yeah. So it would be 1 over.
Yeah, so I'm gonna do this for you, Shams. I'm gonna put the square root of x in parentheses to help you see that that's inside, but I think you were on your way. You said this would be what? 1 over?
Over the square root of x.
Okay, good. Times?
Times 1 over 2 square root of x.
Yes, that's it. Good.
Okay.
So the outer function was the natural log, the inner function was the square root of x. We start with the outer function. What's derivative of natural log of anything? 1 over that anything, right? 1 over whatever it was. Times now the derivative of what's inside of here, which is 1 over 2 root x, because we've been through that a million times now, right? Questions on it? Do y'all agree that I could have written this? Isn't that the same thing? Because these two multiply, don't they? Root x times root x is just x, right? So this would be that would be a more simple answer, wouldn't it? So I'm going to show you something right now. Do you remember I was doing these formulas here and I said that there was one here that was really important right here, this one? I said this comes up a lot, that if you have log, any log, you have x to the r, you can pop the power out, right? Remember that? This is a property of logs. I'm going to go back to this problem now. I'm going to redo this problem. And I want you to realize that this right here is the same as the natural log of x to the half power. Isn't that the same? I haven't done a derivative right now. I'm just rewriting it. This is what y is. Then I'm going to use the property of logs. I'm going to bring this power out front. And that's 1/2 times natural log of x. And now take the derivative. What happens to the 1/2? Comes for the ride, right? Because it's constant out front. What's derivative of natural log of x?
Over x.
1 over x. Isn't that the same as 1 over 2x? I'm just showing you there was a slightly easier way to do that problem if you use the property of logs first. I could not have done that for this one. This is natural log of x, the whole thing to the half power. The property does not work here. You cannot bring this half out because the property says that the power must be, the power must be on the x, not on the whole thing, which is why I couldn't do that here. Okay, we've got about 12 minutes. Let me see something. Oh, we still have more to do in this section. I'm going to give you a few to work on right now. Okay, I'm just going to pull these out of the book to give you some idea of what you're going to be asked. Find the derivatives of each of these. That one. All right. Once you start working on those, see if you can't make any headway. But the thing again is we just have some new derivatives now, right? E to the x, natural log x, a to the x, log base ax. But now we can start incorporating all the rules we've already learned, product quotient chain, within those new functions. All right, let's take some time, then I'll go through these. Just get the raw derivative. You don't need to worry about cleaning anything up. Just get the raw derivative on this. I'm going to start working these out. I am cleaning these up a little bit. Let me know in the poll whether or not you get this. Did you get these answers, or do you see how this is working?
So I have a question.
Yeah, go ahead.
Oh, for example, for number 2, what if we just got to that raw derivative, like you said? Would
Yeah,
that be
that's okay.
acceptable?
Yeah, that's okay. Do you see what I did though?
Yes, I do. Yeah, that turns into 1.
1. And then 1 times that just is itself. And then the 1s went away.
Yes.
So, I mean, yes, you want to be able to find the derivative, but you also want to be able to follow the algebra that I used to clean it up. Okay, we only have like 3 or 4 more minutes. So I want to do one more for you before we go. But your homework for this section, only do 1 through 39 odd only. I mean that don't go past 39 because there's stuff we haven't talked about yet that we'll have to do next class. I really do recommend you try and do as many of these problems as possible, because now we're mixing this up with all the other techniques that we know for taking derivatives, and things can get messy. All right, they can get real messy really fast. So if you can do this homework well, you should feel real good about yourself in terms of your understanding of taking derivatives just in general. So let me give you another problem here. How about if we had this? What if we had y equals 7 raised to the x times 4 raised to the x? You know what? Yeah, okay, we'll do that. So what you need to see here is that you've got 7 raised to this yellow power, right? 7 raised to that yellow power. And so I need to take the derivative of 7 to a power. Well, the derivative of 7 to a power is itself. Okay. But because it's a 7 and not an e, what do I have to tack on to the side of this? What do I tack on?
Natural log of 7,
Natural
I
log
think.
of 7. Okay, so that is using this. Where is it? Where is it? Where is it? Right here. If you're taking derivative of a to the x, it'll be itself a to the x times natural log of a. That's what I'm using. But I'm not done because I've only taken the derivative of the 7 part, 7 to that power. I now need to take the derivative of what's up here, which is a product rule, right? So next to this, I have to do my product rule. So when I do my product rule, I take derivative of the first one, derivative of x, which is 1, times the second one, plus now the derivative of the second one. What's derivative of 4 to the x?
Should be 4 to the x times the natural log of 4.
It's natural log 4. That's the derivative of 4 to the x, 4 to the x natural log 4. But I'm not done. This was a product rule, right? So I still have to finish off by hitting it with the x that was the first function. There's my derivative. One more. Let's say I had log base 4 of x squared plus 1, and I want to take derivative of this. Well, I have log, right, base 4 of this yellow stuff. So I have to start with the log base 4. When I take derivative of log base 4, again, going back to what we did here, if I have log base a, the derivative is 1 over whatever was there times natural log of a. Got to start with that. So this will be 1 over whatever was in here, x squared plus 1. But then I have to do natural log of the base 4. That's the derivative of the log part. But then chain rule says now take derivative of the x squared plus 1, which is 2x. And I could slide the 2x on top. We're out of time. You're going to need to practice and ask for help, ask questions next time. Here's the most common mistake I see. Students will be asked to find the derivative of like 5 to the x. And they'll tell me that the derivative of that is x 5 to the x minus 1. What did they do?
Did a regular derivative.
They did
Or
the
like
power rule.
the power
right?
rule. Yeah.
They did the power rule. They were using this rule, x to the n. The derivative of that is nx to the n minus 1. This is true, okay? This is true if your variable is in the base and your exponent is a number, right? If I do x to the 4th, or let me do it this way. If I do x to the 5th and take the derivative, then yes, it's 5x to the 4th. That's all still the same, okay? But see here, they've switched places. The x is up in the exponent, the base is the 5. They've switched. When you take that derivative, this is not it. It's 5 to the x times natural log 5. That's what the derivative is. Okay, so just be careful. All right, do your homework. See you on Thursday.
Thank you. Bye.
I'm gonna head to my office hours at 4 o'clock.
Thank you. Have a good night.
Okay.